talk, right? Very happy to have Daniel Silvestre here in person. So for all of you who don't know him, he's an associate professor at Nova University in Lisbon and focuses in his research basically on control, right?
Let's keep it like that.
But it's like the fun we talked about it during the break, right? That your context is or your background is actually more diverse. So you started as a computer scientist, computer engineer, had computer networks in your undergrad in Lisbon as well, and moved over to Imperial for advanced computing to end up in your PhD with control, right? So quite a journey.
You get all of that from our talks in this.
And yeah, so in his current research, he applies control barrier functions to several problems, especially also, I think, in the domain of spacecraft. And I think it will be a very interesting talk, right? Looking forward to it. Right. So yours.
I think you can hear me well. So good afternoon, everybody. Thanks for sticking around. So I'll try to skim through a lot of stuff and gain us a little bit of time. So in the interest of that, let's keep on going. So just a brief outline. So I'll start by formulating set control problem. So here you'll see me diverge a little bit of the ideas that have been put forward, at least up until now, because I won't just view this as a design of a safety filter. Then this light background is really, really light, because most of you at this point should know all of this. And then I'll pass through different examples to highlight problems with these CBF designs that I think were not mentioned yet, so that is nice. So let's start. So the type of applications that we are talking about, so here I placed 3 of them, which are kind of the examples that I then use during the talk. So the first one is, let's say that we want to reorient a spacecraft or a satellite. And maybe we have constraints like don't point this optical sensor to the sun, please point this other sensor to a star, so it's like a star tracker, so you shouldn't miss that one. Or we can be doing collision avoidance for in-orbit assembly, docking, and with other bodies that are irregular in shape. So all of that will somehow appear later on. So let me just briefly, so all of you have seen these types of slides. So we are considering a control of fine system later on. I'm actually going to assume that this is written in strict feedback form. So we might just make it explicit the relative degrees of these 2 functions f and g. And essentially this safe control problem is just please get us a trajectory from the closed loop that is asymptotic stable, so that means that this trajectory goes to some set valued point. Sorry, it's not set valued, so set point. And the other part is forwarding that. And I just put it up here because later on I'm going to change lots of things in this slide. So just once again, a light background. And here the only thing that so all of you have seen an equivalence to this. So right now I'm starting with control diagonal functions before I jump to control barrier functions. And so in control diagonal functions, the task is design U vector such that the derivative of the diagonal function then becomes negative definite. So that's what this rho translates. So this stuff right here, as we've seen so far, this is V dot. And this just tells you V dot small or equal, because once you implement this, will put small or equal. Small or equal than some class K function of V, so that induces asymptotic stability. And I want to make it explicit that I've seen this in one of the slides as well, that we are trying to select a U vector from a set of possible control vectors. Then if you look at CBFs, now CBFs is exactly the same, but now we want the reverse. So we want H dot to be kind of positive balance. So we want this to go up as we approach the bound. So you've seen other interpretations. This is my own, so that we treat both of these things in the same way. And once again, we can define a set of all of these control vectors, and we are selecting one of these points somehow. Okay, so you've seen this one. This is kind of the first one, which is we can use CBFs in safety filters. So that just means we want to design a control. So we want to select one of these control vectors that is close enough to some predefined controller such that the CBF condition is satisfied. I haven't seen this before here, so I just wanted to place this in slides. So if you use the Contour, so the KKT conditions for this optimization problem, this is very easy because this is a scalar constraint. So you have one scalar constraint. That means the solution is going to be given by two parts. And so this is essentially the nominal controller plus a correction term. And that correction term is either 0, so that you retrieve the nominal one, or a correction term that comes. So this is very similar to what happens in MPCs, except in MPCs we'll have a bunch of these inequalities, and so we'll have 2 to the power of the number of inequalities of correction terms. The overall part that we are interested in is just keeping it locally reaches in X. And you'll see why I'm writing this in a minute. And so someone said that during one of the presentations, if this is reaches, then it means that we only have one solution for this trajectory. But I'm more interested in combining these with CLFs. So instead of, and here, once again, I'm going to be a little bit provocative, because in the end, it will come back a nominal controller. So I would say here that we are disregarding the nominal controller, but if the original dynamics is in strict feedback form and is not and has relative degree higher than 1, in the end we will do backstepping, and in backstepping approach, the first part is design give me some nominal controller that pre-stabilizes the upper level. And so in the end, you still have a nominal controller. It's just that you don't have a nominal controller for the whole thing. Might offer us a little bit of flexibility. So we are selecting a control vector from now the intersection of these two sets. And we are allowing here this parameter to be like a slack variable, such that we can simplify a little bit the stability condition to always allow for the safety condition. And you'll see that this also arises some problems from the once again, so if we do the same exercise, if we apply the KKT conditions, now we have 2 scalar constraints. That means 4 possible solutions for the optimization problem. So you will write something like this. So we have 3 controllers and 0, because the solution, assuming that we center this Lyapunov function or the function that we put in the cost function, we center that at 0. So normally one of the solutions will be 0. And I just place here what is the algebraic expressions for these 3 controllers. So you can go over this later on if you haven't seen it. Hopefully everybody has. And the point here is that this is all of these controllers, they are algebraic in X. So there's no iterative procedures and so on. So I think that's what made this very attractive. So we heard someone say before during this workshop that the fact that we have very good solvers like GPOAs and all of that is a nice feature. I would argue that if you don't have input constraints, or if you somehow can model them in these CBFs, then you have even better, because that's just an algebraic expression. So now that I've covered that, and just very quickly, because we've seen most of this during the workshop, I wanted to do kind of the same exercise as Victor did in the first presentation, which is let's design these CBFs, the typical one, right? So get me the safety function, then we use that and we pose that it should be a CBF. We calculate the H dot and keep on from that. So before doing that, let's pick again the example of reorienting a spacecraft. So if we are doing this, so you could now view these dynamics. Now these dynamics are in strict feedback form, because the torques are going to be applied to the angular velocity, but not for the attitude. And of course, we can always do backstepping. So that's kind of which is the same as high order. So I don't know, because I've seen in one of the presentations, someone say, well, we need backstepping, but there's a paper, I think CDC 24, that shows the equivalence between the two procedures. So you are pretty much pick whichever you prefer. And so in this type of problem, the idea is drive to some desired orientation, and then maybe we start adding the objectives, right? So the constraints. So maybe we want some to avoid some funny constraints. So you can write that if you are describing latitude with a rotation matrix like an inequality like this, and then maybe we have some constraints like for the angular velocity and for the torque. So we have some maximums for all of those. So if that's so here, I just wanted to give us do a step back and show you an example from the literature of how to solve this problem, but I would argue in a much more complicated way, and with lots of problems, and just to motivate that maybe CBFs and CLFs are nice just on their own. So for this CubeSat of the University of Washington, there's a paper from Maximer's group, which essentially first model the orientation of incoterminants, kind of the same as if you are doing this with rotation matrix. You can argue that rotation matrix have points where they are not defined. I would argue back that quaternions have like parts where double quaternions place in the same part, so you lose some of the theoretical properties. I can also argue that Euler angles, they still have problems, but you can go around. So that's a very rich discussion to be had if we want to make, and it's going to be a preference anyway, I would say. And so, but still, the point is, even if you write this in quaternions, you can still write the type of pointing constraints like this. And so the idea on this work in the literature is that you can split as normally is done in guidance and control. They are using, for the guidance, they are solving this as an optimal control problem with a successive convexification, that's this SCBFs. And then for control, they are using MPC linearized around the normal trajectory. So that looks like this. So they're trying to minimize the error, so they are not, well, sorry, not the error, so the input, because this is the trajectories for the torques. And it's subject to the differential equations. You have the pointing constraints, you have the initial conditions, you have the constraints for the angular velocity and the maximum torques. So you would solve this with successive convexification, but this is offline, so it's fine. And then you can do an MPC to track that. And so here, as you can see, the only thing that is changing is the dynamics that are now linear, because they've linearized around that nominal trajectory that came from the guidance. And I would say that this is a very common way of going about this. And just so that I trash talk a little bit this approach, because we are in the CBF world now. So right now, as you can see, this is a continuous, so this is a problem written in continuous time, which means that once you go to a solver, you have to discretize. And so the way that they do it is they place what they call nodes, which is essentially how many of these discretization points you are going to do for the continuous evolution. This means that the constraints are not always satisfied, because you are now just enforcing on these specific points. In between, they can be violated. So right there, you have a difference if you were doing this actually in continuous time. And then another problem, which is the linearized version might not allow you to track the nominal version. And so you might lose a lot of performance. There are still problems with this, even though we are doing this optimization with the horizon. And so if we now try to do the same thing with CBFs and CLFs, so we started with Euler angles. And of course, there's a slight abuse here, because I'm assuming that this matrix always exists. So this inverse, which just means don't use, so write the angles appropriately to the maneuver that you want to do, such that you don't face the singularity parts. But assuming that we can handle that part, now this is exactly written in strict feedback form. So you have a first part here that doesn't have the inputs, and you have a second equation that has the inputs. So this is relative degree 2. And so with this, the idea with the backstepping would be, so now we are starting for the CLF design, so for the actual nominal controller, if you want, because there is no nominal controller yet. And so you can just select a quadratic function such that we converge the other angles to some desired values. And then for the backstepping, that's where the provocation comes back to bite me, because in the end we still need a nominal control, and you can use anything that is Lyapunov based. And here, as you can see, the controller, so we denoted this with V0 because it's just for the upper part, so it's just for the angles. So it's assuming that you can control the angular velocity directly, and it's just for that part, because everything that comes below that is backstepping. And so in order to do backstepping, we have to use this Lyapunov function that we defined for the upper level. And then this is a very common trick, which is to weigh in the difference between the nominal angular velocity that would be generated by this nominal controller in 20 with respect to the actual angular velocity of the cycle. And so if we then pass to the CBF designs, then we can design one of these candidates for each of the pointing constraints. Then of course the total CBF would be the total safety safe set would be the intersection of all of that, which means that you have to take the minimum of all the CBFs, and the very, again, common trick is to use the log sum x approximation. That just means that I write this operation right here, so the minimum of all of the CBFs as log sum x, as the name implies, of all of the lower level CBFs. Okay, and then of course with this K0 parameter, you can tune in how close you are matching this non-differentiable function minimum. So if we keep on going, then in order to make this into a valid CBF, we have to inspect the H dot and check that it satisfies the CBF constraint. So you can calculate the time derivative for H as you normally do. So you take the gradient with respect to the state, and then you multiply by the time derivative of the state. And then, of course, if you have to assume this type of condition, and then we can essentially calculate what is going to be this alpha that we are going to place here, such that this is a valid CBF. And we can do this because the angles are bounded, so it's relatively easy to do. And so and once again, we need a nominal controller for the top system. And so we are just going to use this controller where the constant that we later are going to design for this part appears here. And then we can keep on going, plug back this upper level controller into the H dot function, check that is always positive, and then using the backstepping, in the end, we can verify that the supremum is always greater than this value. And so, of course, this was, so we were helped by the fact that these angles are bounded. So in general, this is not going to happen. And of course, we can go over the other constraints. So we haven't done all of them. So I can then take so I'm not trying to bounce the maximum angular velocity. And so with that, I could use this typical candidate function of just pass everything to the other side of the inequality. Take its time derivative, do essentially the same trick, and then come up with some function to be placed here, such that this inequality is always verified. So this is a little bit tricky at some point, but at least for this case, we could do this. And in the end, just to wrap all of this together, you can again use the log sum x trick. So this is just to enforce that we only have two inequalities in the QP, such that I have an algebraic expression for the controller, and that this is fast. And so I'll use again the log sum x trick, but now for the CBFs that encodes the pointing constraints, and the CBF that encodes the conditions on the angular velocities. And so in the end, you would get something like this. So if you use the closed loop, So here we started with a very large attitude error, just to check that one. Of course, given the theoretical results, you were expecting this to work. We also tested, what I wanted to point out with this simulation is just that you can start with very large orientation angles as long as you select the other angles the way that you are making them appropriate, so that you don't get that inverse matrix to be simple, so it doesn't exist. And then of course, we can also encode the input constraints implicitly by selecting appropriately these constants, and this is only made possible because everything is bounded. So you just have to calculate the subprimum for that and arrive at some value. We also, this was supposed to change, but apparently it doesn't. So we also tested what happens if you have large pointing constraints restrictions. And once again, that is fine. So it's, as you can see here, the orientation error tries to zero asymptotically, so it's asymptotically stable. And then of course, the torques and the angular velocity, they satisfy the constraints that we placed. Okay. And so the main, before I pass to that part, so one of the main things that I would like to highlight here is that, of course, this guidance plus control approach is much worse in terms of computational complexity. And it's not guaranteed to verify feasibility of the trajectories. Okay, so since we discretize this continuous trajectory in a bunch of points, it might happen that the solution of that is not dynamically feasible in. Okay, and in the paper we actually have like a Monte Carlo run for this. And so sometimes, it's not very often, but sometimes the MPC plus the guidance does not work. So it will violate constraints, and sometimes it gets us a problematic situation, because then in practice we wouldn't have any control action to apply. But what I wanted to point out is that the computational times are it's like an order of magnitude faster for the CBF control. So here we multiplied the computational time, because these were simulated in a laptop, and we were comparing against an application-specific processor, and that has a 2 orders of magnitudes difference in terms of the rates. And so we just multiplied all of the computing time by 100 to reflect on that. So it's a minor part, but the same conclusion still applies. That if you are doing this with a typical approach that is very often used, then you would get into trouble. So with this guidance plus a control for the tracking mode. And so the take-home message of this first part of the talk is, of course, in this case, we were able to exploit this bounded nature of the angles, because we model everything in the other angles. And the CBFs could be designed just by inspection, just by calculating derivatives of H, and then forcing the design of the constants to match the inequalities. But in general, that's not going to work. Then, of course, in multiple CBFs, you can always group them with a log sum X trick. And this is just to maintain computational efficiency in terms of the lookup table that we are going to generate for the controller. And that backstepping allows you to address this issue of higher relative degrees. And even if you have mixed relative degrees, you can use a very common trick, which is control a point that is not the center of mass. So sometimes that is where the mixed relative degree is coming from. But, and I think this is the key issue that I would like to highlight. So if anybody here has attended a presentation related to hybrid systems, your spidey senses should be thinking. Because one of the key features that they use to motivate the use of hybrid controllers is because you cannot guarantee global asymptotic stability for this type of thing. So I must have some problem that I hidden under the table. So let's look into that. So that's the next part. And that problem is exactly undesirable stable equilibrium. So if you use a continuous controller in a space that has obstacles around it, Sometimes these are not very problematic. So here, I'm assuming an obstacle that is just a polytope, and we are designing a CBF based on, so here we don't have input constraints, so since we can do whatever we want with the inputs, is always feasible. But as you can see, if you start really orthogonal to the circle with respect to the target, you'll get stuck in the boundary of the obstacle. But this can be made worse. So if you have this ellipsoid right here that was used to upper bound the triangle, then now you have a bunch of initial conditions that drive to this region. So it's not that, because normally when this is discussed, if we have like circles, one thing that you can say is that in practice you have knots, and so you have disturbances, and so you are not specifically aligned with something. So this is like a negligible problem. But as you can see here, there are cases where that's not going to happen. So you'll have a region of attraction for this undesirable equilibrium. So you'll be safe. So nothing that was said before in this workshop is wrong. So you'll be safe, but you won't be stable. Okay, so that is kind of an issue, especially for polytopes. Then of course you could be thinking, well, I was really conservative in placing an ellipsoid and trying to do a CBF that was just a quadratic function, so Z is differentiable and I can pass everything to the other side. Especially because I talked about the log sum X trick. And so if you look at this one, that's what we did. So we applied, so now we are representing the unsafe set by these four constraints. So being below this right here, being to the left of this hyperplane, and so on. And then of course we can do the log sum X. So you'll get something that is smooth around this polytope, and it should be fine because it's just a small difference. And then of course you can tune this with that parameter kappa that appeared in the log sum X. So if you crank it up to almost infinity, so a very large value, this gets closer and closer to the square. But you still get the same issues. So you get a bunch of initial conditions that drive to the desirable equilibrium. And the same thing still happens with the triangle, but now it's just a single point that is right orthogonal to this point. So that is kind of an issue. And so we wanted to solve this issue. And so in order to do that, we need to go for a hybrid controller. So what does that mean? So if assuming you might not have seen hybrid controllers, so that just means that we have some dynamical equation for the flow. So the flows means when the system is running in continuous time. For that, we are augmenting the state with some variables that were going to be used as the logic of this controller. And then at discrete times, there will be a change in the dynamics, and that is governed by something like this. So at that time, something changes discretely, and then we go back to a continuous evolution of the states. And so now the matter is, how do we define when we do the jumps, so that we differentiate between the flows and the jumps, and also how we design this switching. So the switching logic, in order to do that for a polytope, the way that we went about this is now we are thinking about the polytope as just a lot of constraints to be inside, so to be on the left or on the right hand side. But you can generalize to these for 3 dimensions, for instance. And the point is that we will be storing kind of a set point in between. And we'll also be storing which of these hyperplanes is active. So which of the CBFs is now we need to take into account. And the way that we are going to select this next half space that is safe is just taking the maximum of the evaluation of the CBF. And so as long as we design properly these X hats that tells you where you are going to drive next in between, and we avoid limit cycles in this decision and so on. So as long as this produces just one way towards the destination, then we can also prove that it is a global asymptotic state. And so the way to do that, at least the way that we followed, so that there's multiple ways you could achieve this, but we use a concept called synergistic diagonal functions. So the idea is produce kind of a hysteresis between when you do the jumps. And so we are at the safe half space, and we are only going to jump when we are, in quotes, sufficiently safe inside the next safe half space. And that prevents us from jittering between CBFs when we are running these inputs. And so now the jump set just requires that the system drives to the next subset before we do the next flow. And the only thing that is required, as I was saying, is that the definition of this safe half space is still valid. So once we do the shift, you are still okay with the new CBF, and that is kind of used with this X heads. So there's a lot of ways that you could design this X head. So I won't go too much into detail because you can this is being presented in one of the sessions in this conference. But at least the way that we are going about this is just so we are going to design. I'll talk a little bit more about that during the conference. But another part is, can we guarantee then that these QPs will always be feasible regardless of the jumps and the flow sets and all? And so in order to check where are these problems, it means that we need to check when the intersection is at. And that is true when this is at. And so as you can see here, the problem is when you have alignments with the gradients of the Lyapunov function and the barrier function. And so in the end, we know that there is a relationship for this lambda that depends on the magnitude of these vectors. And so if that's true, we can use this value to select later the constants for the CBF and the CLF such that this set is not in. And so that's exactly what you can do. So you can plug the value of lambda back into the inequalities. As you can see, now the CBF inequality will be bounded by something that was from the CBF inequality, but also by something that is for the CLF. And that is just because now the vectors are aligned. So we replace one by the other. And that means that in the end, we will get an inequality for what this class K function needs to satisfy. And so we can appropriately select the two class K functions, so the one for the CLF and the one for the CBF, such that this is always feasible. If that's true, then we are good to go. And that is, so here is just one option. So of course you could play around this, but if you select gamma to be just 2 times one constant, if you select alpha to be another constant, and if you make the constants satisfy this inequality, then this is okay. And then, of course, for handling input constraints, one option is, of course, you can place the constraints in the feasible space of the QB. That's always an option. Or you can also adopt something that has been proposed in the literature in the last 2 years or something, which is called the optimal decay QB, which means that we also have another optimization variable that can be selected by this quadratic program. And that is going to adapt the evolution of this CBF. And so if this is running in continuous time, you are kind of changing, adaptively changing the class K function that you use for the CBF. So normally that handles the inputs, but if you can, of course, can always place the inputs right there and be done with it. So what does that look like? So if we use this controller now, so here is just to warm us up before before I show you an example more related to space applications. So here we use the unicycle because it has mixed relative degrees, because the rotation, so the variable that controls the rotation does not appear in the same number of derivatives of the CBF as the linear velocity. But of course, as I was saying before, a trick that was known in the community about Lyapunov-based control was to just control a point that is slightly above, slightly in front of the center of mass. And if you do that, you resolve that issue. And so following this, so here you can see 2 similar initial conditions, but one of them will be driven to the left, the other will be driven to the right. And this just is just a result of that maximization that we've seen before. In order to always not be problematic, the point is the solver needs to give me one option. And so if we do that, so here you can see the evolution of the index. So this means which of the CBFs, so which of the facets is active at each time. So you can see when we are driving downwards, it means that at some point, this is so the fourth CBF is the one that is being used. So that's why the index jumped to 4. Whereas when we are driving here, so at first, this is the CBF that is being used, then one of them goes for this one, the other one goes for this one, and so it keeps on switching. And the important part is that there are some X hats here in between that guarantee that you can switch, and once you switch, you don't keep on switching back and forth. So you don't have these single type of behaviors. That is a problem in hybrid systems because, well, you are comparing numerical values. So if you are doing if this is equal to that, then that would be an issue, and of course with noise. To avoid that, we have kind of this safety almost guarantee that you first need to be sufficiently safe inside the new half space before you can jump to that half space. Okay, sorry, this wasn't moving. Okay, so as I was saying, we are going to be using this for space rendezvous in the invited session on Wednesday morning, so you can definitely check that out. So I will guide a little bit more about how we do this design for these actual problems. But right now, let's just use the example to see what happens. And so here we are assuming we have Earth or whatever is the central body, have a chaser, we have a target. We are going to write the dynamics in the LBL frame. So it means that we are centering everything in the target. And the chaser dynamics is just this expression. So the only part that I really care about is that now this is in strict feedback form because you have this first outer loop, and then you have the new loop, which depends on you. So we are finding that. And so the objective here is that we want the chaser to dock inside this non-convex region. That is our objective. And do this non-convex shape of the target. The idea is we are still going to split this mission into 2 stages. So the first stage will be the rendezvous phase and then the docking phase, which is, I hope it's enticing to the community because we are keeping the same nomenclature, same type of phases for this. But now this is a single hybrid controller that we use throughout, and then the CBFs and the CLFs are going to be changed. But you'll see that the same type of nominal controller for the upper level is still, we are going to use the same one. So what does that mean? So for the rendezvous controller, the idea now is we are going to take the convex hole of that target body. So essentially, I'm going to place here something like this. And so I'm just going to take this polytope. And now it's just exactly what we were doing before. So we have this hybrid controller design that is going to be changing between the CBFs that define each of the half spaces. It's going to use the synergistic Lyapunov function so that we don't have zero behavior. So that's the trick. So in the end, if we follow exactly the same procedure, we will end up with 2 inequalities. So if we are going for the docking phase, it's much easier because we don't need the hybrid part. Because now, once we are inside this target region, this is a convex region, so it just means don't leave these boundaries. So we can just enforce that with a log sum X trick. And that's exactly what we did. So we just converted all the whole polytope and to be inside by the log sum X trick. And now we still have the same format for the controller. Is the only difference is that the functions are different. But in the end, when we are going to do this backstepping design, we'll get here this nominal control. So still get that. And so this is what it would look like now. So now this is the target, so it's moving relative. So the distance is not representative, but it was just to have this idea that now you're seeing the movement of the target. And we are assuming, so, and you'll see in the next part of my talk, that the idea here is that we can control just the point mass because we can always enlarge the polytope by doing the Minkowski set. So we'll touch that in a minute. And so, of course, here I'm starting in the same orbit, but just behind the target. But you can also start in a different orbit if you close. So on the left-hand side, you have the orbit. On the right-hand side now, you'll see the relative positioning between the target and the chaser. So you will see the chaser appearing from above, and then doing the docking, just using that controller that I was describing. And so some extra info. So we actually went to the literature and used this nominal controller, just because it would be a nice fit to use something that already, in this case, we kind of minimizes acceleration. And as you can see, there was another orbit that we tested. So now an orbit that is closer to Earth than the target, but we always manage to avoid the obstacle. Here you can still see that the switching that is happening between the hyperplanes that define the shape of the target. And then, of course, you have the inputs and the error of the position asymptotically trying to do. So the take-home message from these parts, I'm just missing one part. So the take-home message here is that you can avoid, so you can render the closed loop globally symptotically stable, so you can avoid those points of indesirable equilibrium at the boundary of the obstacle. If you are a little bit clever on how you design this switching for your hybrid control. And the other interesting feature, I would say, of course, we always kept the control law in a closed form expression. So this is an algebraic expression. Of course, we are approximating a little bit because the log sum x, whenever you use that, you are not exactly using the polytope, you're using something that resembles the polytope. And we can check and design these compatibilities just again as I was doing in the controller. So you calculate when this intersection is empty and you keep on exactly the same steps. But there's still a main challenge, that's the third part, which is up until here, I've always told you what is exactly the safety condition. So I told you we want to avoid this cost. And so that is known a priori at design stage because we had to design the CBF to make that happen. And so now what I want to do to bring this back home is construct that from an observer. Okay? So in order to do that, I'm just going to go back to the first slide that I did about this light background. But now the problem is that we don't have a safe set that we want to make forward invariant. What we'll have is a set valued flow. So now it's kind of a set that morphs in time and represents the estimates for the obstacle. But this means that we need to update our definitions. So the CBF now, it means that we won't have a fixed set that we want to make forward invariant. So now we have a set valued flow. Of course, the CBF will have to have time as well in the domain. So you just add here time. And then the same condition applies, but you will get, when you take the derivative of h with respect to time, you'll get an extra term, which is the derivative of h with respect to t. But the same type of thing applies, so you still have the same type of set for the physical space. And we could, of course, do the same thing for the CLI. So both of the designs for us, it's kind of the equivalent. And then, of course, you could still bring a safety filter, just adapt everywhere where you have now functions of h, just add the time variable. Of course, here you don't see the difference because I encapsulated everything in this h dot, but there is the derivative of h with respect to time plugged in there. You could also write the closed form expressions for this. So now you get exactly the same format, except that everything will depend on t. And of course, you would like to make this continuous in t, so that everything is well behaved as before. The same goes for, sorry, I don't have that. So because I thought I had for the QP, but it's exactly the same. So if you have a CLF and a CBF, just adapt all of the definitions to also have t in the expressions. So now if we go back to the safe navigation problem, so we will have some nonlinear dynamics, and now I want to explicitly take into account the fact that the vehicles, they have bodies. And so I'm saying that the ego vehicle is some center of mass plus some convex shape that I call here B bar. And the same happens for the obstacles. So the obstacles will have a center of mass and some convex shape that represents its body. And the idea here is we are assuming the dynamics to be linear, but we just submitted for an LCSS paper when the dynamics are nonlinear and uncertain. So it just means that the observer needs to be defined differently. But here this makes way easier to present the way that the observer works. Okay. And so the problem formulation just means that we want the shape of the ego vehicle to not intersect with the union of the obstacles. That's kind of obvious. And so, as I was saying, in order to avoid the collision, we can also deal just with point masses, because I can add the shape of the ego vehicle to the shape of the obstacle. And so the only thing that I'm missing now is to construct an observer that tells me a set to contain the obstacle, then convert that set to a CBF and just plug that in the hybrid controller that we were having before. And so the way that goes, as I was saying, so now just means that the trajectory for the center of mass of the ego vehicle should not intersect with the union of the obstacles. And the evolution of this set for the obstacles is just going to be a transition matrix times the previous state. And then this means Minkowski sum of sets. Here you have the transition matrix, but for the input, because the input is unknown, so it's just a set W. And then in the end, I'm also summing the shape of the obstacle and my shape in reverse. So if we do that, a way to construct this, as I was saying, is that we need a set representation that allows me to do all of these set operations exactly. And we need a method to convert this into a valid CBF. And then, of course, we can always use the logsum text trick whenever I have multiple CBFs and I want to join them into a single one, and apply backstepping to handle this relative order group. And so, if you're probably not aware of set valid estimation, but this means that I only need to allow for linear maps. So if my description allows me to represent this operation, then I'm fine. I should also allow for Minkowski sums to be written exactly. And this is generalized intersections, because in the end, I will intersect with the measurements. So if you've never seen this, think of this as the predict of the common filter. But now all these sets represent the support of the random variables. And instead of doing an update, you are doing an intersection with the supports. And so with that, we'll move very fast through this, just so that you get an idea. So you could start with intervals. That set representation means that I'm doing a morph of a cube, but with a diagonal matrix. And the point is, I can still not represent generalized intersections. If you think of a zonotope, that is a linear map of a hypercube, but now G can be any matrix. So you'll get something that is symmetric with respect to a center point. If you think about ellipsoids, that's just a projection of a sphere, so an L2 unit ball. If you do constrained zonotopes, now means that I get here an intersection. And so now I can get stuff that is not symmetric. And if I do, so this is just the polytopes, just to highlight. And something that I've been working on, which is this definition. So this is a data structure to represent convex sets. And I can represent weird sets that are Minkowski sums of LP. I can represent intersections of polytopes and ellipsoids, and I can represent intersections of ellipsoids. And so with this, the first part is ticked, because all of the operations I can do exactly in this data structure. And the second ingredient is the observer. So we could do the recursive observer that I just told you, so predicts plus update same as in the common filter, but that means that these data structures keep on growing. The other option is that we can use a finite horizon backwards and use a one variable observer to construct the set for n time steps before. So if I do that, all of these data structures, they have exactly the same size, so it just depends on my horizon n. So that is very useful to the conversion that I need to implement. And so how does that conversion go? So now I have a set that is a linear map of a larger state space. I have a cut. Have I gone over the 45 minutes?
Oh yeah.
I thought I was going to be fast, sorry, but I'm really close. It's you have a linear map, you have a linear cut in this higher state space, and now we have these inner variables stored in these simpler sets. So what we can do is we can use the QR decomposition to write the parametric solution for this equation, rewrite the set like this. So I'll just go over very fast so that I don't take too much time. Now you can think of each of these constraints as being a CBF on its own. I can plug back the expression for the variable to get the full expression of the CBF, and then I can do the log sum X trick to get a single CBF that represents being outside of that whole set. And so if we do that, in the end, I just need to do a projection. So that means I have to solve an optimization problem, but that is fairly easy. So we were taking 3 milliseconds per obstacle per sampling time with the quasi-Newton method that ships with MAPA. So most likely with some other method we can get better. And so this is the final part. So this is what you would get. So now we have a guaranteed safety. We also have stability, asymptotic stability, because we were using the hybrid controller, and these white shapes around it. That's the estimate that we are considering. So that's what comes out of the observer. So here we just use for the single integrator the nominal controller up, but we could also use this for second order system. So that's that part. So here we use this nonlinear system with kind of a gravity term. We are still using obstacles that are double integrators with random acceleration, and we're getting the same. Okay, and so with this, I kind of conclude my talk. And so the point that I was trying to make across is that, first of all, we have lots of problems that we can solve if we now tackle both the stability and the safety. So we could do this safer, the base for safe reorientation. We could use hybrid controllers to enforce global symptotic stability, so to avoid this undesirable equilibrium. And we can use observer based on sets to generate the sets in continuous time that we then avoid with the hybrid controller. And so with that, I think that's all it. So just a shout out to Google, which is a current PhD that worked mostly on the topics about CLF and CBF controllers, and to Francisco, which was a former postdoc that worked on the part of CCG observers. And with that, just the references for the papers that are being presented here. So they are fairly recent, and thanks for your time.